Hello all of you. Welcome to the 25th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about evaporators. First single effect evaporators, then multiple effect evaporators. In the last class, we have discussed some problems where we can get analytical solution for the evaporator problems. But in many cases, as you may realize by now, is that solution is not possible and we have to look for numerical solutions. So today I will discuss one of the methods for numerically solving this evaporator problems, particularly multiple effect evaporator problems, that is called Badger-McCabe method. So let me begin with whatever equations we have obtained for a triple effect evaporator forward feed, probably 2 lectures ago. And we have assumed that the heat transfer coefficients are the same and the heat transfer areas are the same. So we essentially have 3 energy balance equations and 3 heat transfer equations, and of course there are 3 other solute balance equations, but that is kept separate because the mass fractions are appearing only in this last 3 equations. They don't appear in the first 6 equations, right? The general method which I proposed was try to get these 6 variables from the first 6 equations, and once you have that, then the mass fractions can be gotten from the solute balance equations. And of course, we have property relations, and again I emphasize that this lambda 1 and lambda 3 is the latent heats. They are not really constants, they depend on temperature, and there is a high degree of nonlinearity possible in these 6 equations, right? All right. So what does the Badger-McCabe method does is basically it starts with some guessing of some variables, and then it works in an iterative fashion to improve that guess, right? So let me begin with the drawing of the triple effect evaporator. I will not write all the variables, but just so that you get an idea of what we are doing. So we have in triple effect evaporator, I am using the vapor of the first one to heat the second one in the forward feed. The same also happens in the reverse feed as well. And second effect, the vapor feeds the third effect, right? But in the forward feed, the feed enters the first effect, and in reverse feed, the feed enters the last effect. But we are doing forward feed right now. The liquid of first effect enters the second one, and liquid of second one enters the third one as feed, and the liquid of third one is the final product, and the vapor of third one is the final product, final vapor, right? So we have T1 P1, T2 P2, T3 P3, and the temperature and pressures are decreasing along the effects, right? So the choice of variables that we have taken as unknowns are S, T1, T2, L1, L2, and A. And the way it has been chosen, you can notice that I cannot get any of the variables directly from any of the equations, right? So let us say, for example, I am looking at the first equation. Then what is unknown in the first equation? F is known to us, Cp is known to us, T1 is an unknown, S is also an unknown. So we have more than one unknown. So I cannot get anything out of this, right? Of course, L1 is also an unknown, right? And keep in mind that lambda 1 also depends on T1. So T1 is an unknown here. So all of these are unknowns, right? So we cannot eliminate anything from here. We already have eliminated the vapor flow rates, but now we can no longer eliminate anything else. We can, there is like so many unknown variables in this equation. In the second equation, T1 is unknown, T2 is unknown, L1 is also an unknown, and L1 is an unknown here. T1 is unknown, so lambda 1 is unknown, and lambda 2 also an unknown, and T2 is unknown, so lambda 2 is also unknown, right? So we can go ahead and try to look at each of that equation, and you see that it is highly coupled problem, right? Let us say here S is in fourth equation again, S is unknown, A is unknown, and T1 is also unknown. So everything is so coupled together, we cannot sequentially do it. For the single effect evaporator case, I have shown an example where we can solve the equations one by one and get the solution. In this case, that is not a possibility. We need to simultaneously solve these equations. And I again emphasize that these equations are not linear in nature in general. These are non-linear equations. You may have learnt about solution of linear set of equations, and we'll discuss some examples. Those are easier to solve, right? So we have equations in the form of Ax equal to b, right? And we can compute the matrix inverse and get the unknown things. That is not possible here. It is a system of nonlinear equations in general. So therefore, we need to think about some alternative strategy of solving it, right? So that one of the alternative strategy is to guess some variables, right? So let me propose a strategy that's given by Badger and McCabe, where they have guessed T1 and T2 to begin with, right? So T1 and T2 are the guess variable. TF is known, TS is known, and T3 is also known, right? So this is a very smart choice of guess variable. We will discuss in detail in the coming lectures why this particular choice is a good choice, right, when we discuss the graph theory and things like that. But for the time being, let us assume that T1 and T2 is given. If you think about it, the overall temperature drop starting from the steam to the final product is my delta T overall, that is Ts minus T3, and this is known to us. This is already known to us. T1 and T2 are unknown, and I am guessing it, right? So overall drop is known, but the drop happening in the first and second effect, delta T1 as Ts minus T1, delta T2 is T1 minus T2, and for that matter, even the third effect, delta T3 is T2 minus T3. So these temperature drops are not known to us, and when we guess something, we will have an incorrect statement of incorrect value of those temperature drops. So this method, this iterative method, basically starts from this notion that we know this overall temperature drop, and I will obtain some temperature drops which will be anyway incorrect because I have guessed my T1 and T2 value, but then I will somehow redistribute this temperature drops in order to develop an iterative scheme or to find new guess values for T1 and T2, right? That is the overall idea. So we will guess these. Once we guess this, then we will be able to solve the equations maybe. And if we do that, then in that case, I will get wrong values of temperature drops, then I will correct it and I will get new temperatures and so on, right? So now, let me say that if we have guessed my T1 and T2, I want you to focus on the last three equations, the heat exchange equations appearing here. So we have S lambda S is U A Ts minus T1. Then we have F minus L1 lambda 1 is equal to UA T1 minus T2, and we have L1 minus L2 lambda 2 is equal to UA T2 minus T3, right? So in these equations, what is going to happen if I do not have the correct value of T1, T2 and T3? Clearly, if I am trying to get area from there, we will not get the correct value of area, right? So let us say I get area from the first equation and second equation and third equation here. If my T1 and T2 and other values which I have found are correct, in that case, all the equations, all the three equations will give you the same value of area. But if my T1 and T2 are wrong, then I will get different values of area and wrong values of area from the three equations, right? So let me label that wrong value of area as something, right? If I indeed work with wrong values of T1, T2, so for correct T1, T2, this should happen. For wrong T1, T2, I can still divide S lambda S by U into Ts minus T1, but I will not get the correct area, I will get a wrong area. Let me call it some A1. And the second one will give me F minus L1 lambda 1 is equal to UA2 T1 minus T2, and then L1 minus L2 lambda 2 is UA3 T2 minus T3, right? So only when T1 and T2 are correct, we can get the correct areas from all the three equations. And if it is wrong, then we will get different areas from the three equations, and they will not be correct, right? So now we already have a way to figure out whether a given value of T1 and T2 are correct or not. If they are correct, right, if they are correct, then T1 should be, A1 should be A1 should be equal to A2 should be equal to A3 is equal to whatever area we have. Anyway, the area is unknown here, right? If A1 is equal to A2 is equal to A3, what does this mean? It means that we have correct value of T1 and T2 in the problem, right? So we should start with this guess value of T1 and T2, and we should do something that basically approaches this particular limit, right? And as long as we are able to do that, we can have some sort of an iterative scheme. That is the first point that is used here, right? Now, let us look at the first three equations. We had 6 equations in total. Let us look at the first three, the energy balance equations, right? What are those equations? FCP TF minus T1 plus S lambda S is equal to F minus L1 lambda 1. Let me just stop here. My unknowns originally are S, L1, L2, T1, T2 and A. That's what I started with. But T1 and T2 I have guessed. So for the guess value T1, for the guess value I know T1 and TF is not an unknown, F is not an unknown, CP is not an unknown. Now the only unknown here is still S, right? And TS is also not an unknown, right? And my L1, right? So F, S and L1 are only the unknowns here. Lambda 1 is defined at T1, but T1 I have guessed. So provided we are going with the guess values, the only two unknowns in this problem are, in this equation are S and L1, right? Let me do it for, so the unknown here now are S, L1 for guess T1, T2. Second equation, we have L1 CP T1 minus T2 plus F minus L1 lambda 1 is equal to L1 minus L2 lambda 2. Again, I know T1 and T2, whatever guess value I have. L1 I am not knowing, L1 I am not knowing, and L2 I am not knowing. And since I have guessed T2, I can get lambda 2 from there anyway, right? So I can get lambda 1, lambda 2. These are known to us. Only L1 and L2 are the unknowns that we have, right? Similarly, for the third one, we have L2 Cp T2 minus T3 plus L1 minus L2 lambda 2 is equal to L2 minus L3 lambda 3, and again T3 is not an unknown, so I know lambda 3. L2 is still an unknown and L1 is still an unknown, right? So now you see we have these three equations and all of them are in terms of three unknowns. Here again we have unknowns L1 and L2. So if I now solve these three equations, I can get S, L1 and L2. So let us solve again simultaneously because it is coupled, but simultaneously solving three equations is easier than simultaneously solving 6 equations, right? Let us solve simultaneously to get S, L1, L2 for guessed T1, T2, right? Now, once I have done that, I can go back here, and I can compute the areas A1, A2, A3, because now I know S. Now I know S here, I know lambda S because Ts is anyway known to us. I know U, I know Ts, I have guessed T1. So now I can find A1 from here. Similarly, I can get A2 and I can find A3, right? So I can compute A1 and A2 and A3 from there, right? So now we have a scheme. So we have actual unknowns are my S, L1, L2, T1, T2, A. So first step, I will guess T1, T2, and second step, once I have guessed it, I can use the three energy balance equation, the first three equations we had, to get S1, sorry, S, L1 and L2, and this will require a simultaneous solution, but only of three equations. And now use the three, I would say modified, because I have replaced A with A1, A2, A3, use three modified heat exchange equation to get A1, A2 and A3, right? Now I want to use these areas somehow to update my temperature values. That is the key part, because if I can do that, in order that we can approach A1 equal to A2 equal to A3, that is my final solution that will give me the correct value of temperatures, right? So what I do here is I have already defined temperature drops. Delta T1 for the first effect is Ts minus T1. Delta T2 for the second one is T1 minus T2. And delta T3 for the third one is T2 minus T3. So what I am going to do is I am going to say that delta Ti new is equal to delta Ti old into Ai by A, for I is equal to 1 to 3, right? I don't know the A as well, this is unknown here, but you will see that will not matter, right? So I have a way to update the temperature drops, right? My temperature drops are also wrong because my guess value of T1 and T2 are wrong, but I have a way to update that, and this will give me a new value of the T1 and T2. Let me look at the first one, for example. So I have Ts minus T1 new is equal to Ts minus T1 old A1 by A. So for the old value, whatever I started with, I will get a new value of T1 from this equation, right? But I don't know AI by A, right? But what I know is my sum over I of delta Ti, that is my Ts minus T3, and that is anyway given, right? And no matter what guess I am doing, I am anyway satisfying that. Whatever T1 and T2 I choose, if I sum them over, whatever T1 and T2 I choose, if I sum over this delta T's, that sum, we will have the cancellation of T1 and T2 and we will still get Ts minus T3, right? So, we will use this fact. So, I know, I have just said that delta Ti new is equal to delta Ti old into Ai by A, and now I also know that I can sum them over to get the overall temperature drops, and that will give me something like Ai delta Ti old by A, right? And this is something known to us. This is my delta T. This is known to us, right? That is delta T overall, that is equal to Ts minus T3. So, I can use this to find the value of A. So, A is now my delta T. So, A is now my summation over I, Ai delta Ti old by delta T. I already have computed A1, A2, A3, and therefore I can get the value of A. Keep in mind that this will be a wrong value because I have guessed T1 and T2, so it will not be correct value, but nonetheless I can plug it in the equation that I have just got, and this will give me something like delta Ti new is equal to delta Ti old Ai divided by summation over I Ai delta Ti old into delta T, which is known to us, delta T overall. Okay. So, now I have a way to update my temperature drops, which means essentially updating my temperature values, because temperature drops can be expressed in terms of T1, T2 and T3, right. So, and I have a way to update that after this, right. So, update T1, T2 using this equation, and this is my, I can say, third step. I already have, this is my fourth step, right. I already have computed S L1, L2, I already have got A1, A2, A3, and now in my fourth step, I am going to update this T1, T2 using this equation, and now I will stop if A1 is nearly equal to A2, nearly equal to A3. Whenever we are doing a numerical solution, we don't go for exact thing because that will take forever, right. But whenever the areas become more or less equal, we can pretty much stop, right. How much error do we tolerate? That depends on what is my requirement, but typically as soon as we are running into differences in 6th decimal, then we can pretty much stop, right. So, we can say that when this become approximately equal, or we sometimes say that we basically converse, right. So, what you will see if you are running the code, in the first iteration the areas will be very different. In the second iteration, the three areas A1, A2, A3 will be somewhat closer together. In the third iteration, they will be even more closer together, and maybe after 20 iterations they will be pretty much same but differing by 6th decimal or 7th decimal or things like that, right. So, then we will stop. right? Because there is no point keep on doing it once we have approximated the answer to a good approximation, right? So this is the method that is called the Badger-McCabe method. There is another way of solving this equation. We could have written the set of equations that we have differently, and in terms of essentially a vector of variables x, which is my unknowns s, t1, t2, l1, l2, a, and a vector of functions fx, which are coming from the 6 equations here, f1, f2, f3, f4, f5, f6. That could also have been a possibility, and there is a way called Newton-Raphson method for multiple equations that we can apply in that case, and we can get the solution for that. We will discuss that method for this particular example when we discuss the numerical solutions of equations in week 7. So with that, I want to conclude the discussion on evaporators. In the next week, we'll start talking about heat equations in the class. So with that, I want to stop here. Thank you so much.